So we're here at the MAV TV 500 with Little Fuse Speed to Design program and mechanical engineer Hilary Pouchak. Welcome.
Thank you.
So you've been having a blast here with everybody, but we learned chatting with you offline that your work is actually incredibly fascinating, an extension of which was featured, in a sense, at the Olympics this year. Tell us a little bit about it.
I'm a 30-year practicing mechanical engineer, but 20 of those years is in a highly segmented field called lower limb prosthetics. And I'm proud to be associated with some of the first fundamental designs that were utilizing carbon fiber. Carbon fiber composites is heavily used in the race car technology. So I was quite fascinated to come here and experience and see the applications of what they're doing in IndyCar. But in the prosthetics world, myself and a small core group of people engineered and devised the first lower limb prosthetics out of carbon composite and utilize it in a dynamic bending fashion rather than, in most cases, like here, even in the race car technology or in aerospace, which is rigidity, lightweight and rigid structures. Yep. We take composites and utilize their high strength and energy storing potential and to use them in a dynamic bending environment. And so we devised essentially what is referred to as energy storage, lower limb, foot, ankle devices. And you mentioned what was really kind of a culmination after all of these years of working here is for the first time, at least in the real public eye, at the London Olympics, a bilateral amputee, Oscar Pistorius from South Africa, was running on the carbon blades, the cheetah blades that we call them, that I had a hand in designing. I was one of the chief principal engineers working on that project.
I want to know, with Pistorius, obviously, and some of the competitive runners there, they're using it in competition and they're running really, really fast. They're in incredible shape. But is that a device that you could use if you were a double amputee but not an athlete?
Those devices can be configured in different ways for different levels of amputations, different capabilities of certain patients, and so using energy storage lower limb prosthetics is really fundamental in bringing back something that has perhaps been lost from that individual.
But it doesn't necessarily rule out an electromechanical solution, right?
Not at all. Not at all. My expertise in this particular technology I work with is really simple mechanical designs, and that's really the novelty of it, is to try to get simple mechanical function in novel designs without a lot of complexity that can really kind of function independently of powered systems or intelligent systems, electronic systems that really are starting to come out more today. You'll see the best usages of that sort of stuff in upper extremity prosthetics, in hands and arms and elbows and things like that, where you need power. It is a bit of a, if you want to say, a conflict right now on whether or not there is high value to these electromechanical systems that can be used in lower limb prosthetics, but it's being done by some very specific talented people right now, and they're getting closer to using that because sensor technology, accelerometers, force detectors, pressure sensors, all those things are now becoming miniaturized, the control electronics, and I think there's going to come a point in time where now we'll be able to start to utilize that in very similar fashion that we're using, the great characteristics of carbon fiber composites in lower legs and foot ankles.
So with carbon fibers, it is easy as sort of mixing it up, putting it in a mold, and you're done. I can't imagine it's that easy.
No, it's very similar to the same technology here. Is that carbon fiber itself is a very stiff material, very strong and tensile, and what is done, of course, is to try to get that to be impregnated into a matrix, and a resin matrix of epoxy or some sort of adhesive, and that's how the term composite comes up. So in the case of in race cars and even in the artificial feet, is that carbon fiber, very thin and small, has to be oriented. And it literally is almost like the grain in wood, is that if you take the grain in wood, is that if you bend it across the grain, then you'll find that it has its enhanced stiffness to it. If you try to go against or aside to the grain there, or perpendicular to the grain, then you're going to get a very weak structure. So very similar with carbon fiber. And so the manufacturing technologies is to take that material and to orient it into plies, pretty much like a phone book, and then stack these plies up. You may orient them in different positions and get different characteristics of that. In the case of these sprinting feet, like what Oscar Pistorius is wearing, it's a very highly engineered tapering structure which changes the deformation of it under load. And so you'll get different types of bending dynamics based on where the load is at any point in time.
Well, thanks for coming out on the track and sitting here in 102-degree weather and telling us about your technology. That's great.
Happy to do it, Brian.